Hello everyone, today I want to prove to you why the row space is an orthogonal complement to the null space. So hopefully this will be helpful for some of you that are having trouble visualizing this theorem, because in my textbook this was left as an exercise to the reader. Okay, so the best way to show this is with this matrix here, where we have a leading diagonal of 1s except for the last where we get a row of 0s. Okay, so how do we find the row space? Well, let's call R the row space. The row space has two row vectors, which forms the set R1, R2. Okay, and it's pretty obvious to see that this set is comprised of I, standard basis vector I, and standard basis vector J. Okay, and hopefully you can see that here. If we look at the dimension of this basis, so the dimension of dimension of the row space, which we'll call R, is going to be 2. So this is R2 that we're talking about. Okay, and the span of this, if we draw a 3D coordinate grid, because that's going to be helpful. The span of our row space is all of R2. So this is going to be R space. So all combinations of, and I'll draw R1 and R2 as well. So here's R1. Here's R2. And you notice that any linear combination can get us maybe like this vector R here, okay? But we're never going to get a vertical component. Notice that. It's all in the plane. So we can't get vectors like this, okay? And that's important, as we'll see later, because we're going to find out that the null space is actually just z vectors pointing upwards. Okay, so let's find what the null space is now. So the null space is defined as x equals 0. So the span of this, the homogeneous system. And if we look at the homogeneous system, it's already in as row reduced as it can be. So it would look something like this. And let's interpret the results, because this is actually a big struggle point for some people. They'll see this system and they might make some weird assumption just for getting the basics. But remember, what this is saying is for any pair x, y, z, the homogeneous solution vectors is going to be 0, 0, and z is going to be any arbitrary number t. It has no effect on the system itself. Okay, and why is this? Well, if we put z into here, here, or here, any t we output, or sorry, any z we output is literally just going to be 0. So if we call z t, well, for all z, it's always going to be 0, okay? Because it will always equal 0. So what does this mean? Well, this means that if we go back to here, our null space is going to be any vector that's like this, okay, pointing straight up into the air. So let's just draw a couple vectors here. If you kind of remember multivariable calculus, it looks like a vector field that's fluxing through a plane almost. But yeah, so these blue vectors, this is the null space. This is a good way to imagine it. So hopefully that's a good visual of why row space is orthogonal to null space. And if you use more complex vectors, and let's say you find that matrix A has a dimension of 2 and the null space has a dimension of 1, you're going to find this orthogonality quite often. And it's a very visual way. And of course you have higher dimension, but you can't really visualize that. So that's all I wanted to show today. I hope you guys enjoyed this proof. If you did, please drop a like, comment, subscribe. Have a wonderful day. Bye-bye.